All right. So I think we should start. The most secluded room in entire IIASA complex, only for a few selected. So this is the welcome to the session about uncertainties in SSPs, interpreted and the biases, uncertainty in scenario-based assessment ensembles. So my name is Massimo Tavoni. I'm from Italy at the RFF CMCC European Institute on Economics and the Environment, together with Céline Guivarch from CIRED and Ben Sanderson from Cicero. We organized this first session motivated by the need looking at scenarios ensembles and understanding better to what extent uncertainties are indeed fully represented in those ensembles and how those ensembles should be interpreted and what can we learn about robust courses of actions against those uncertainties, whether those uncertainties are on the climate side, on the economic impact side, whether on the technological development, whether on the transition mitigation side or adaptation side. It's pretty clear that uncertainties abound on many respects, and I think we want to use the opportunity to have these large ensembles to make justice of these uncertainties without reducing them, and also in being able to interpret and communicate it effectively. So that's more or less the topic of the session, which will be followed by another session, which is actually very closely related, led by Carl and Yoeri. So it's just two short mini sessions, 45 minutes each, but actually more or less very much on the same topic, I would say. And so to keep it very short, we have 3 presentations, and these are going to be mini presentations in these mini sessions. Let's say 8 minutes if we can manage, with a couple of minutes and Q&A per each. So that will leave at least kind of 10 minutes at the end, since we're starting a bit later, for a bit of a discussion. Great. So we have Thomas from CIRED first. Then we have a recorded presentation, I believe, and then another slide. We have uncertainty on the top of the presentation. Yeah.
Thank you. Good evening. I'm delighted to be here to present our recent research on entitled "What Can We Learn from the Way Milestones Are Sequenced on the Road to Net Zero?" It's a study within the Navigate project. Since the Paris Agreement, the international negotiation have focused on the way to achieve the main goal, and with several issues to be discussed. And beyond national commitment and strategies, a part of the upcoming international. Okay. Thank you. So a part of the upcoming international negotiations aim to bring out some coalitions on specific targets or milestones. As an example, 6 months ago, at the Glasgow Pact defined a collective objective towards the reduction of fossil fuels and around specific, so with the wording that I have put in this slide. And in my presentation, I intend to show how scenario ensembles can help discussing and defining such milestones. So we used the RRC scenario database, which includes around 3,000 scenarios. And we focused on some temporal characteristic of the scenarios and to analyze how the milestones are connecting each other. So we applied a sequence analysis approach. A sequence is a succession of states or events, and the social science have developed some methods to compare and analyze sequences, which are inspired from the analysis of DNA sequences. And so sequence analysis include a set of processes to analyze, compare, and cluster, for example, sequences. In our case, in the case of climate change studies, and in this study, we defined as state or event the 12 event or milestones that I have put in this slide, and they are defined by threshold. For example, on the left you have 8 milestones that are defined by the reach of halving, for example, primary energy production from coal, oil, or gas, or and then we defined a second threshold for each energy, which is a diversion by 10. So it's what we called a quasi phase out. And we also analyzed 4 other milestones, which are the moment where the AFOLU sector reach negative emissions, and 3 other milestones for the capture and storage of CO2, from CCS. So we apply this method for exploring the implications of delaying coal phase out. Here are some first results. We compared here the median year of reaching a halving of the coal use in primary energy, and the year of dividing by 10 the coal use in primary energy in black. And we compared through the different targets, the scenarios divided in three targets of 1.5 degrees low overshoot. They are called the C1 in IPCC in the IPCC report, 2 degree target and more than 2 degree. And what we can see is that the halving of coal use in primary energy intervene 9 years sooner than, for example, in the 1.5 degree than in the 2 degree scenarios. And it's quite the same when we focus on secondary energy and so electricity production from coal, but with even sooner years. So it's a first result, but it's quite well known. And what was a bit more interesting and new in our study is that we tried to understand how the different milestones are connected. So here you have in gray and black the milestone of coal use. So you have the legend beside, but and the first finding that you have four sequences, 4 cluster of scenarios, for all for 1.5 degrees C, and they are clustered through an algorithm which try to find the most differentiated sequences of milestones in terms of order or lengths of different states. And so what we found that is that we have a first sequences. The first finding comes from the fact that across these groups, the halving of primary energy and electricity production from coals occur before 2030. So you have you have the purple and gray and black milestone that occur at the first time and before 2030. And then you have a first, you have 4 parts. The first one is at the bottom, it is the coal phase out, which is in black, does not occur. It's just the only one where it doesn't occur. And at the same time, we can observe an early and quite massive development of CCS with 2 milestones reached before 2044. And this result is very high. This result in a very high amount of cumulative CCS compared to the other groups. You can see that on the right here. Yeah, thank you. And the second pass from the bottom of the figure, the coal phase out occurs in 2032, which is the earliest across the group. Then we can find 3 other milestones before 2050. The halving of primary energy from gas in 2037, the capture of 5,000 megaton CO2 from CCS technology, and the halving of primary energy from oil in 2048. And in the third group, the first effort on coal phase down is early too, but with especially a phase out from electricity production in 2031. And then the overall phase out occur almost 10 years later. So, okay, so I will continue. In the last group, the coal phase out occurs in 2035 and is followed 5 years later by the development of CCS and 10 years later by the reach of net negative emissions in the 8-follow sector. I have only just 1 minute to finish this presentation. The halving here is the same picture with 2 degrees C consistent scenarios. And what you can see is the halving of primary energy from coal occurred generally a bit later in the representative sequences consistent with but there are again the first milestone to be reached across different milestones. We can also notice that in 3 of the 4 representative pathways, there is a convergence of the year of coal phase out between 2038 and 2040. We have also one path where there is a high amount of CCS, so it's the bottom one. So there are preliminary results of this exploratory study. So the main conclusion is this study shows again first how stringent is the phase out from coal using primary and secondary energy, and second, the consequences of delaying this phase out in terms of the other milestones to reach quickly. In terms of methods, this exploratory study seems to bring a new reading grid of the scenario ensemble that could inform the discussions around milestones. I have pointed some methodological issues too, but we can discuss them later in the discussion. Thank you.
I would say in the interest of time, I would say add all the 3 presentations since they are short, and then we can have discussions at the end. Make sure that and I don't know if Jennifer, she's online.
I'm online. I don't know if you can hear me, but I guess you have my recorded presentation.
Yeah, we can hear you well. So I think
okay.
I think the standard practice is to have the recorded presentation.
Okay.
And then if you can stay online, Jennifer, then for Q&A at the end.
Yeah, I can stay. And if we hold questions to after all the speakers, I'll still be here for that.
Huh? Yeah. Okay, so it looks like there's no audio, but since you're online, then you can present it yourself and I can move the slides for you. Just bear in mind the 8 minutes, Jennifer.
Okay, sure. Yeah, all right. Let's see. So yeah, sure. My name is Jennifer Morris. I'm a research scientist at the MIT Joint Program on the Science and Policy of Global Change. And the work I'm presenting is combining integrated assessment modeling, Monte Carlo analysis, and scenario discovery. And it's work that's presented in the paper that's there on the bottom of the slide. You can advance the slide, please.
Yeah, just a sec.
Sure, yeah.
Here we go.
I'll keep talking in the background. Yeah, so socioeconomic development pathways and their implications for the environment are highly uncertain. Typically, this uncertainty is modeled through scenarios such as the SSPs, and they're represented as ranges resulting from model intercomparison projects. And here, or an alternative approach is uncertainty quantification via traditional probabilistic Monte Carlo analysis, which is what I employ here. What we do in this paper is we model uncertain input variables, such as the cost of advanced technologies, energy efficiency trends, fossil fuel resource availability, and others as uncertain. And we also model some climate parameters as uncertain. And we sample from those distributions. We run them through our integrated models along with assumptions about the policy conditions or the long-term temperature pathways. And as a result, we get integrated probabilistic scenarios. And so if you advance, please. Yeah, and so this approach creates distributions of key results, things like emissions, temperature, GDP, different sectoral results, energy, and a slew of other outputs that we now have some probabilistic representation for to give insight into the likelihood of different outcomes. Advance, please. And so a strength of this approach is that it fully and systematically can explore the uncertainty space compared to using a limited number of scenarios, and it can provide insight about the likelihood of outcomes. However, a limitation is that the distributions for each outcome are characterized separately, and so relationships that may exist over time or among outcomes are lost. So you don't know by looking at the distributions alone whether like the high end of one outcome is consistent or would occur together with the high end of another outcome. If you advance, so here we use scenario discovery to address this limitation. Next slide, please. And so scenario discovery involves a set of tools, essentially for screening large databases of model simulations to identify outcomes of interest and their conditions for occurring. It's often paired with robust decision making. So if you go starting over on the left side of the screen, you can see there are uncertain inputs. And again, they're typically sampled without assigning probability distributions. Those samples are run through a model to create a simulation. And then some outcome of interest is identified, and usually a threshold for that outcome. And then machine learning classification methods are used in order to map the outcome of interest back to the input ranges under which those outcomes of interest occur. So if you go to the next slide, please. And here we do a slightly different take. First, we apply this approach to probabilistic ensembles. I think advance again. I think I have animations here, sorry. So now the uncertainty yeah, that's great. The uncertainty inputs are probability distributions. And so when we create the simulation ensemble, they have a probabilistic interpretation. And the second thing we do differently is to focus on how endogenous outputs are related to one another. So now we're taking a main outcome of interest and its thresholds, but then looking at other endogenous outcomes that the model is projecting. And we're using those same types of machine learning classification methods to map the main outcome of interest to other outcomes. And so we're looking for different storylines that might be prevailing throughout the ensembles. So if you go to the next slide, please. So as an illustrative application, I've applied this approach to look at US GDP growth, concentrating on both high and low US GDP outcomes, looking at the 90th percentile and above and the 10th percentile and below. I think you can advance through the rest of this slide. Yeah, and then exploring relationships to other endogenous outcomes, including GDP in the rest of the world, emissions in different sectors in the US, and levels of different types of energy within the US, all under a 2-degree scenario. And we can do this for other scenarios as well. Next slide, please. Yeah, that's fine. Great, so to set this up, on the x-axis, we have our outcomes starting all the way on the left to with the main outcome of interest, which is US GDP, followed by the other endogenous outcomes that we're interested in. On the y-axis, we have the percentiles for those outcomes. And you can also see the absolute max and min values for each on the top and bottom. And then we take from our whole ensemble, we find all of the scenarios that line up with that are the 90th percentile of US GDP growth. I think we're going too far ahead, but that's okay. And all of the scenarios that are the lower 10th percentile of US GDP growth, and we can map them all onto a plot like this. So we can see how each individual scenario falls in terms of all of the outcomes. And where they fall in the percentiles maps back to the actual distributions of the full ensemble. So we can do this and see all of the, low US GDP outcomes. I think if you advance again, you'll add in all of the high US GDP outcomes. And then we can see where these, the red and the blue are diverging. And where they diverge suggests that that outcome is most closely related to the main outcome of interest, which is US GDP. We can also make distributions for the high and the low combinations. I think if you hit, there, for each of the subsets of scenarios, and you can see where those distributions diverge. Again, that means that that variable is more closely related to US GDP. So I think if you advance, there's some, so these show like the importance of, in this case, US non-electricity sector emissions are important drivers of US GDP. When you have to reduce more emissions and outside of the electricity sector, you tend to have lower US GDP. We see a negative general relationship between US GDP and GDP in the rest of the world. And then one more advance, please. And in terms of energy mix, we see many combinations of energy that can be consistent with a US GDP outcome. There are some general tendencies, for example, higher amounts of renewable energy. You can see the red lines being generally higher for renewables, being more consistent with high US GDP. But I think if you advance, there's many different combinations that can occur, and that's fine. And then the other thing we can do with this type of approach is try to identify individual scenarios that are defined by specific combinations of outcomes that we might be interested in. And we can look for scenarios that might have counterintuitive results that we want to investigate further. Here I've highlighted some just as an example. And then we can dive further into what's behind those scenarios. I think if you advance again, sure, that's fine. And then one more, I think this is the last slide. Great, you can put all those up. So the idea of this approach is that by combining the probabilistic ensembles with these scenario discovery techniques, we can explore these full ranges of outcomes with associated likelihoods, but also maintain intact individual scenarios and information behind them. And by doing so, this type of approach can help avoid potential biases in perceptions of what we think needs to happen to achieve a certain outcome, because we're exploring this broad space. So you can challenge some of your assumptions, like does super low emission scenarios need to have high amounts of renewable penetration? We're exploring spaces where that might not be the case. It also allows us to try to identify prevailing storylines and identify individual scenarios we might be interested for specific studies. And it can be used to aid in the development of a smaller subset of scenarios that are purposely designed to include a wide variety of possible futures or span a particular range of outcomes of interest. So this is a different take on kind of how to explore this a large uncertain space without specifically ahead of time designing a set of illustrative scenarios. So I think that's all I have for the slides, and I look forward to the discussion. Thanks.
All right, great. Thanks, Jennifer. So we'll come back to Q&A in a sec. Before, last not least, we have Chris Smith from University of Leeds. IIASA. Great.
Okay, thanks very much. So yeah, I've got the stopwatch on. I'm going to talk about downweighting similar scenarios in IAM model ensembles. So I'm very pleased that Jennifer's already talked about the diversity in scenarios, and I'm actually going to show that actually our existing set of scenarios aren't particularly that diverse. Okay, so why downweight scenarios? Well, actually, just like climate model projections, the population of IAM scenarios represents an ensemble of opportunity. So what I mean by that is we're not necessarily spanning all possible futures, what could potentially happen, but at the same time, we might be oversampling some possible futures too. And robust methods for assigning weights to climate model projections already exist, and Ben Sanderson has published extensively on that over the years. I'm going to show that the scenario database contains a high degree of duplication of scenarios, and this could potentially bias key messages such as the rate of decarbonization required and the date of net zero required to meet Paris Agreement targets. And actually, this isn't necessarily a new concept in, say, IPCC reports. So in the special report on 1.5 degrees, there was a group of 13 scenarios from the AIM model that were excluded for they would assess to be too similar to other scenarios from the IAM. So they were removed from the assessment of net zero dates in table 2.4. And rather than sort of take an ad hoc approach, we're seeking to look for a sort of a more numerical statistical way of actually assigning a similarity score to different scenarios. So what we do here actually is we actually take from the physical climate science a very similar approach. So normally we sort of we look at in physical science, we look at metrics such as global mean surface temperature or precipitation or Arctic sea ice. What we're doing here instead, we're looking at IAM derived variables such as emissions, GDP, and energy system variables. And we choose 14 variables across what was called tier 0 in SR 1.5. So these were variables that IAMs had to report in order to be included in the database. And we assigned each a weighting, which is sort of this ratio of scenario quality divided by scenario repetition. The scenario quality is very simply applied here. We just use the SR 1.5 method of saying, does the emissions of the scenario come within the 2010 assessed uncertainty of greenhouse gas emissions? And if yes, we say it gets a quality weighting of 1, and if no, we say 0. The scenario repetition is the more sophisticated metric, and this is done using a root mean squared score for 14 variables. Based on how scenarios are projecting their pathways between 2020 and 2100. And this is this sort of fairly complex sum here is basically assigning a weight to repetition. We could take more sophisticated metrics for the quality, for example, looking at how well scenarios have performed over the last 20 years with regards to emissions and energy system variables. But we're keeping it simple for the purposes of this. So the 14 variables that we assess, we break down into 4 groups. So we have emissions, economy, mitigation, and energy. And some variables are given more weight than others. So this is kind of normalized by 120. So what we actually do is these actually sum to 1 in the paper. And you can see that we sort of put more weight on CO2 than we do to other emitted species, primarily because CO2 is generally the dominant climate forcer. And in terms of the energy system, we weight we make energy demand as the same as primary energy variable. So we kind of put equal weight on energy supply and energy demand. I should say as well that these weightings are subjective. This is not necessarily a unique way of doing this. And we also, for each of these variables, we define a radius of similarity. And this is the right column here, and it basically says how similar to another scenario is considered too similar. And the metric we use for this is by comparing SSP scenarios between so different IAMs. So for all of the IAM scenarios, 5 or 6 SSPs would have provided projections, and we take the smallest RMSE between pairs of SSP scenarios and different IAMs as our radius of similarity. And we say anything that's closer than that is probably too close. So what happens when we actually apply these weightings to the SL 1.5 database? Well, firstly, we find that no scenario has an independence weighting of 1. So there is some repetition, even small repetitions in between scenarios. We find that quite a lot of the highly duplicated scenarios, the ones with these low independence weightings, are baselines. This can be explained because these baseline scenarios are identically the same for mitigation variables. For example, they have a carbon price of 0 and they don't include any CDR. But what interestingly we find is that these 13 AIM scenarios that were excluded from SL 1.5 for the assessments of net zero year actually are not the most duplicated, even over in the class of lower 2-degree scenarios. And possibly even more interesting is that out of the 5 below 1.5 scenarios, so those that remain below 1.5 without overshoot, 2 of the 5 have a very, very low independence weighting. And what happens if you effectively sum the independence scores? We claim that out of the 381 scenarios in SL 1.5, there's effectively about 133 independent pathways. So to show you what some of these duplicate scenarios look like at both ends of the database range, on the left here we have from image we have 4 baseline scenarios that are almost identical across the 14 variables. The 2 I haven't shown here are CCS and carbon price, which are identically 0. And on the right here we have those 2 C-road scenarios that are assessed as below 1.5 degrees. You can see that there are fewer variables available for these scenarios because they didn't report everything that was required in the database. The way we get around that is to reweight the relative categories for each scenario. And you can see that, again, these 2 scenarios are effectively identical, apart from a slight difference in the CO2 emissions. So what happens when we apply that to the year of net zero? We actually find that this below 1.5 category, actually the median year of net zero, when you apply the weighting, shifts forward 6 years from 2044 to 2050. Now, obviously, there's a big caveat with that in the sense that there's only 5 scenarios in that category, so any small effect is going to substantially change that assessment. But actually, when we sort of look at the larger categories of 1.5 low overshoot and combining all the 1.5 consistent, we find that weighting actually affects the net zero year by 2 or 3 years, ends up being 2 or 3 years later. When we apply that to the 2-degree scenarios, we actually find that the net zero year actually moves forward by 3 years for the lower 2 degrees and by 9 years for the higher 2 degrees. So scenario weighting is actually having quite a large effect on the date of net zero in these scenarios. So finally, my conclusion slide. There exist many near duplicate scenarios in the SL 1.5 database. When we apply weighting to these scenarios, we sort of see a median net year shift 2 to 3 years later for 1.5 consistent scenarios, but several years earlier for 2-degree scenarios in the SL 1.5 database. And I should claim as well that the method we present is subjective. It's not a unique solution. And there are kind of several ways that you can do this. So we're looking to update this for AR6. We're preparing a paper, and also there's nice things you can do with this, including integration with tools like PyAM in order to apply these weightings to the database as part of climate assessment pipelines. So thanks very much.
All right. Very interesting and much needed. Thanks. So the session has ended just in time, but maybe we can ask the next guys for 5 minutes, cutting into your session since we started a bit late, for burning questions to either presentations. Let's give priority to the floor here. Yeah, Jessica.
Yeah, I had a question for Chris, really interesting. And your results are, I mean, and you said it yourself, your results are influenced by these weights. So did you experiment with different weights. And I mean, one thing that comes to mind is some of your variables are just a result of other variables. So the CO2 emissions from fossil fuel and industry is the result of primary energy mix and industry use. So would there be a way to make your method more robust by choosing different variables and making it more robust to the weighting?
Yes, thank you for the question. So yes, we have not yet looked at different weightings or different variables. I do agree. I think by taking a different subset of weights or a different subset of variables and comparing the results, I think we could come up with a more robust result to determine that. And you are correct in some variables are related, such as primary energy from coal and CO2 emissions. I think at the same time, I'm a simple climate modeler. What I really sort of care about in the end is the emissions. I think it's really interesting to actually sort of look a little bit deeper in the scenarios and see what's influencing the final emissions and see at the end of the day whether there are different pathways of reaching what effectively are the emissions scenarios that we come up with. That's kind of the motivation behind that. But yeah, very good points. And we should certainly look at some different measures of robustness.
Yeah, thank you. Nadine Menges from Geomar. I'm an Earth system modeler, so a little bit foreign here. And I have a question to Jennifer, but a general remark to all the presentations, because you looked at 3 metrics from the climate system, which was climate sensitivity, ocean heat uptake, and aerosol forcing. The latter 2 are linked directly to the climate sensitivity, but the absence is the carbon cycle uncertainty and the kind of development of carbon sinks. And that I was missing again in the other talk, like there's no talking about the carbon cycle here. So I'm a little bit confused and maybe, no, that just only determines CO2 concentration. So yeah.
Maybe Jennifer, this is for you. No.
Yeah, sure. The caveat for my work is I did focus primarily on socioeconomic uncertainties. So the number of uncertainties in the climate system that we captured were minimal. So you saw the 3, you called them out. We do have an intermediate complexity Earth system model that we run all of our emission scenarios through. So we do have things, a lot more dynamics within the carbon cycle that we could represent as uncertain. But because the focus of my work was more on the socioeconomic human system side, we minimized the uncertainties on the climate system side. But you're absolutely right that more could be represented, and this approach could be applied to additional uncertain parameters.
Yeah, thank you. I would encourage you to do that because it also is linked to the zero emissions commitment, which is going to be interesting for net zero.
Yep, great point.
Although in the past, uncertainties analysis have been done on all parameters, and some of the socioeconomic drivers actually turn out to be, even more important than the climate parameter or the carbon cycle parameters. So not to dismiss the importance of that as well, of course. All right.
I think that's an important point. There's recent work too that reemphasizes the importance of the scenario in the overall uncertainty, even in the climate system outcomes. So thanks for making that point.
Yeah, last question.
Sorry, just a layman stupid question. I don't understand why in the conclusion for Chris' presentation, why is it 2 to 3 years later for 1.5 degree, but several years earlier for 2 degree scenarios? Why?
Yeah, to be fair, that's a very good question. I've not actually looked at the why. There are obviously, for example, the 2 scenarios from C roads significantly biasing the 1.5 assessment. So if you downweight those, then your remaining 1.5 consistent scenarios become later. So effectively, what you're doing is when you look at the distribution, you apply a weighting, and then you sort of take a weighted median or a weighted range for your net zero date. But as to why, I have to admit, I'm not completely sure. I think it's an open question. If you look at the particular scenarios that are doing what they're doing, then it's possible with AR6 there'd be completely different conclusions. So it really depends on which scenarios are being included.
All right, thanks. We took already too much time from the other session. Thanks to all the speakers. That was really great.